Okay, so it's a great privilege for me to chair this session and to introduce our distinguished speaker for the Distinguished ICTS lecture. For the set of Measure Zero people who may not know Ofer already, to say Ofer Zeitouni is a professor at the Weizmann Institute of Science and also a global distinguished professor at the Courant Institute of Mathematical Sciences, having also had previous positions at the University of Minnesota and at the Technion. So he's, of course, an eminent probabilist that we all know and who has made seminal contributions to numerous areas of probability, including large deviations and random matrices, on which he has written 2 classical texts, and as well as motion in random media and logarithmically correlated fields, on which he will talk today. And it's a particular, he's also a wonderful mentor for many postdocs and students. And I count myself privileged to have been one of them. And so here's a little memento that I would like to introduce.
Thank you. Okay. Thank you, Kavita. Thanks to the organizer for giving me the opportunity to speak here. It's always, for me, it's a pleasure. It's my 3rd or 4th visit to Bangalore, and I really like coming back. So thanks for the invitation. Also, I would like to apologize. Some of you may have heard a version of this talk. I know at least of one person, maybe more. So sorry about that. My goal today is to give some kind of overview to a theory that has been developing in the last decade. Of course, it builds on things that were done before, but it has seen a lot of progress in the last decade. Next week, I will give a slightly more technical talk on one aspect, one corner of the story I'm going to tell you today. So what is this talk about? I'm going to talk about extremes. So for us, extremes are just high values or maxima of random processes, maxima and near maxima of random processes. And in this talk, I'm going to discuss a particular class of processes that are, in a very loose sense, constructed from contributions at many scales. Basically logarithmic in the size of something, usually the size of the system, of the parameter of the noise or something. The number of scale is usually logarithmic in the size of the system. And the contributions are more or less independent from all these scales. Of course, this is never really the story, but ideologically, this is the story. And in different models, you have to find where the ideology is hiding. That's always going to be the name of the game. So where does this show up? So it shows up in a certain class of PDEs related to wave propagation. So that's a Fisher KPP, Kolmogorov, Piskunov, and someone helps me. I always forget. Will be written later. In the study of a particular type of Gaussian fields called the Gaussian free fields, that they appeared in the last lectures very briefly, in the critical dimension, in certain combinatorial problems related to random walks, specifically the cover time of a certain class of graphs, in random matrices, recently in the study of the Riemann zeta function, in certain 2-dimensional polymers, and there are more. So it's really, I mean, some of these things were clear a while ago. Some of these things became clear only recently. And we have really a long list of examples on which we can play this game. Okay, so to put things in context, let me start with a classical situation that is essentially an undergraduate exercise, which is the following thing. So suppose I have independent IID random variable, Gaussian centered, and for all sorts of scaling reasons, I want to give them variance n. And then suppose that I take a large number of such variables, specifically e to the power n variables, and I want to understand what is the maximum of this collection, okay? So that's an undergraduate exercise, because what you can do, well, what is the probability that mn is smaller than a certain normalizing constant an plus z? They are IID, so if the maximum is smaller than that, then all of them have to be smaller than that, so we get that. Well, they are Gaussian, so we can write the expression. And of course, this expression, if an is large, this expression is close to 1, so it's natural to write it as 1 minus Pn times e to the power n, and Pn is roughly the expression that I wrote here. Okay, so far I have really done nothing. The only thing I've done is, okay, this is not really an equality, this is a near equality, and the only thing I've done is to replace the exact expression of the Gaussian. No, actually, sorry, this is an equality, but in the next step, I'm going to make it a near equality. So if an goes to infinity linearly, then Pn is essentially this quantity. You can check it by expansion of the error function. And if you want this limit to be non-trivial, you have not too many choices of an. You must take Pn to be e to the minus n, roughly, up to a constant multiple. And therefore, your an should be essentially this quantity. I don't expect you to do the computation, but I'm sure that each one of you can do it on a piece of paper. So with this choice, if you plug it in, what you get is that the probability of mn is smaller than an plus z is just converging to a particular distribution called the Gumbel distribution, okay? And I've chosen the constants in such a way that everything will work well. Okay, so what do we learn from that? First of all, that there is a limit. Second, that it is of this particular form. And in fact, there's a classical theory of extremes going back to the 40s or even earlier, and you can look it up in the book of Gnedenko, for example, that tells you that if a limit exists, it will be one of 3 types. And Gumbel is one of them. There are several other, but I don't want to discuss other types, okay? So that's a computation. And I remind you, this is what we did. And now what you could also ask is, suppose that I put them, I add some geometry. So suppose at this point, somehow I draw them as a lattice in Z2. And I only draw those points where the value is large. By large, I mean close to the maximum. Okay, then of course, what you will see is something like that for different values of Z. So those are the points that are higher than a certain value of Z. You will get something like this. And of course, this must be a Poisson process, right? Because it's independent, it's essentially independent Bernoulli trials. So what you'll get in the limit is some kind of Poisson process on this unit square. Okay. So that's completely classical, and there is not much I want to add to it. And now to the first example where things are different, but eventually not so different. So this goes back 90 years now to work of Fisher and Kolmogorov, Petrovsky, and Piskunov. That was the name I was missing. And what they were looking is motivated by some applications in biology. This was this equation, propagation equation, with initial conditions F, where F is bounded between 0 and 1 at least at this discussion. Now, you note that when u equals 1 or when u equals 0, this driving term disappears. This non-linearity disappears. And it's not too hard to convince yourself that the solution, if you started between 0 and 1, will remain there. And what Fisher showed is that this equation has many traveling wave solutions. So what is a traveling wave solution? It's a solution of the following form. You take a V, you look at a single function of x minus tv, you plug it here, then of course the derivative in t and the derivative in x are the same up to a product by v. And the WV will satisfy a one-dimensional boundary value problem that you can solve. And what Fisher showed essentially is that there is a solution for every v which is large enough. Not necessarily bounded solutions. In fact, there will be only one which is bounded. The critical one is going to be bounded, the others. Okay, so, whoops, you warned me. So, so if you start, so in particular, what KPP proved in addition is that if you start from a step initial condition, so this black line, this is a step initial condition, and you take a velocity slightly larger than square root 2, then you will be close to 0. So if you look at time t, but at a location that is slightly larger than square root 2t, you will be close to 0. On the other hand, if you go at a location which is slightly smaller than square root 2t, you will be close to 1. So you should really think of this front as this step function beginning to build up a front and eventually converging to some, that's also part of the result, that this front eventually converges if you center, for example, if you center around the value 1/2, this will converge to this traveling wave solution. That's part of the result, okay? But the thing that they did not do is to find out the precise speed in which you go. So this is a speed up to an error which is linear in t, and you could ask, okay, that's very nice, but how does it progress? Okay. So this, of course, does not look related at all to my warm-up exercise. What the hell is a relation, and why do I, a probabilist, tell you about PDEs? So the answer is due to this gentleman, Henry McKean, who gave a probabilistic interpretation to the solutions of this equation. And what McKean did is to say that if I look at the solution, so if U were not here, we know all in this room that U has a solution as expectations with respect to Brownian motion. What McKean showed is that this nonlinearity forces a solution to be expectation not with respect to Brownian motion, but rather with respect to a more complicated object, which is a branching Brownian motion. That's the first process that I want to introduce that is not a simple IID or Brownian motion process. So what is a branching Brownian motion? You start at time 0 with a certain particle at x. So here it's branching Brownian motion starting at x. The particle that you started with performed a Brownian motion. Then an exponential clock rings. When the exponential clock rings, so by exponential clock, I just mean a random variable which is exponentially distributed. When it rings, the particle splits in two. This 2 is related to the 2 in the U square. And then you restart. Each particle begins, you kill the old particle, each new particle begins its own Brownian motion, which is its own clock. And this thing propagates, okay? So after time t, you have roughly e to the power t particles, so a huge number of particles, hence the scaling I chose in e to the power n in my warm-up computation. And this is a simulation where time is going this way, space is going that way. And you see, this is the first particle, this turquoise colored particle. And then it splits and then it becomes a mess. You cannot really, the number of particles grows very rapidly and you cannot really track individual particles, but you get this kind of cloud, okay? Okay, so at time t, the particles are xi of t, and this is what appears in McKean's formula. Okay? And it's not very hard to convince yourself that this formula should be true, at least formally. Just take one particle, evolve for time delta t, and then tell yourself, okay, in delta t, there are two possibilities. Either I did not branch, which is most likely, in which case I'm just a Brownian motion, so this will give me a Laplacian, or I branched, and then suddenly I have two independent copies of the same process, so this will give me a U squared. Okay, so if you take a piece of paper and write down what I just said heuristically, you'll get this equation. And okay, so, okay, I explained to you that why a probabilist talks about PDEs in a probability talk, that's fine, but what is the relation to extremes? Well, if you take so this is the interpretation, if you take the initial step condition, then after space inversion, you can convince yourself what is written here is that all the particles that started at x have to be smaller than 0. After a certain space, moving x to minus x and using symmetry, what you see is that U is nothing but the tail or the distribution, the 1 minus the distribution function of the maximum of the xi's. Because essentially, because you're asking for all the particles to be below a certain level. Okay? So the solution of KPP becomes a question of the study of the maximum of this system of particles, okay? Which is the same question as I asked in the beginning, except that the particles are not independent. For example, two particles at time t that have split at time t half share the common Brownian motion up to time t half. Okay? So this is a correlated system. There are roughly e to the t particle lives, and let's say the positions at time t are xi, and mn is a maximum. So if they behaved as if they were maximum, then the maximum would look like that. That was my warm-up exercise. And the question is, does it apply to BBM? For a while, this was an open question. And here comes the next protagonist in the story. So this is Bramson in his thesis. And what he showed is that the answer is no. Namely, the correction term, so actually, it will appear here in just a second. So this was our back of envelope computation. So you should trust me that I did not miss a 2 or square root 2 or something in the computation, but this is correct. And you see this constant changed. So something is going on. We already know that. In addition, a few years after Bramson, Lally and Selke gave a description of the limit law, and the limit law is not Gumbel. The limit law has an extra, we call it shift. There's an extra random variable, capital Z, which they characterized, such that the limit law is really the expectation of e to the minus z, e to that, which means that it's Gumbel plus an additional independent random variable. That's really what this formula tells you. This additional random variable is just the log of z. Okay? Because this you can rewrite as e to the minus square root 2 x minus z, minus log z. So you're really shifting the maximum, which is Gumbel, by an addition and an extra randomness. And if you think about it now, in retrospect, it makes sense. Because all the particles have in common, for example, the path of the first Brownian motion up to the splitting time. And that's common to everybody. So that's kind of additive to everybody. Okay? So it's not super shocking, but still. And we will call such laws randomly shifted Gumbel laws. Okay? So that's a story. And as part of this story that I told you happened in the last 10 or 15 years, a lot more is known. In particular, we know how to, not only what does a maximal particle, where is a maximal particle, but imagine I want to ask where is a second maximal particle, where is a third maximal particle, etc. And if I drew that as on the line, say, would it look like a Poisson process or not? And the short answer, which I don't want to get into, is that we understand that fully. It's not a Poisson process, but there is an underlying Poisson process that governs it. And in fact, it is a randomly shifted, decorated Poisson process. So you have a Poisson process, which you then shift by this variable log z, and then each of the points of the Poisson process you replace by a certain independent IID random process by itself. Okay? So there is a complete description of what is going on. And, and this talk is about understanding. Now, of course, how are these particles correlated? So if you think about the genealogical tree, you will realize that as you go down on the genealogical tree, you have more and more common ancestry and less particle of this common ancestry. And this is related by a logarithmic transformation because the number of particles is exponential in the length. So it naturally creates a logarithmically correlated field in the sense that in each scale, you get more and more, you get randomness from different, if you think of different generations, you get different randomness, and this randomness is common only for particles that share the same ancestors. Okay, so this is log correlated particles, and this is the explanation of what I tried to say. So if you want correlation theta t, you have an exponential in 1 minus theta t such particles that share this correlation. And there has been a lot of progress. I wrote some names. Here are some pictures, but okay, I'm not going to. And since this slide was done, there are additional names. So now let me give you, so we saw one example in which the bottom line was that we had a shift which does not correspond to IID variable. And this came not in the leading order, but in the second order. Then we got something which was tight. So basically we had a linear shift, then a logarithmic shift, logarithmic in t, and then we had something of order 1, and this something of order 1 we understood. Okay? So the question is it an accident? Does it occur in many other examples? So what I want is to give you several examples where the same picture is known and several others where part of the pictures is known. So what you see here is a plot of the Gaussian free field. By the way, I didn't say it before, but you see, none of the pictures are mine. It's all stolen. And so this in particular is stolen from Scott Sheffield. The previous one was stolen from Matt Roberts. So this is an image or a simulation of a Gaussian free field, a discrete Gaussian free field, which means I'm only looking at lattice points. I'm building a Gaussian process, but only indexed by lattice point and not by the continuum, with Dirichlet boundary conditions. So what does that mean? What this means is I'm just looking at this joint distribution, e to the minus sum of neighbors in the box of phi x minus phi y squared. And one can check, essentially, because what is written here is a Laplacian, is a Dirichlet form associated with a Laplacian, and the inverse of the Laplacian is a green function of the random walk, that the covariance, which is exactly the inverse of the matrix that would appear here, is just the green function of the Laplacian in that box with 0 boundary condition. So at least for x, y in the bulk, it behaves like this log. Hence, now we have a reason to call it log correlated. It's now a Gaussian field whose correlation functions behave like a log. Okay? And this is specific to 2 dimensions. Let me emphasize that. Because a green function of random walk in 2 dimensions is log. In 3 dimensions, it will not be logarithmic. It will be something else. And now we can ask about the maximum, same type of question. And the answer to that, the leading order was computed maybe 20-some years ago by Bolthausen, Döschel, and Giacomin. And they showed that they computed the leading order. And trust me, if you try to compute the leading order for IID random variables with that variance, like we did in the very beginning, you would get the same answer. So to leading order, what they proved is that you get the same answer. And then in a series of papers with Muri, Bramson, and Jian Ding, we proved that you have the exact same expression where the expectation of Mn has the same 3/2 here. This square root 2 is coming from scanning, but it's essentially the same type of result. So again, compared to the IID case, in the IID case, you would have here 1/2. Okay? And again, you have a random variable z, and you get that. So it's exactly the same story. Okay? So that's an example. Now really justifies the name logarithmically correlated field. And we get the same result as before. And is it an accident? So no. So in fact, the fact that it was a Gaussian free field was not so important. What was important is the logarithmic structure of the covariance. And indeed, for a wide family of log-correlated fields that are more or less homogeneous in the sense that the local picture is the same everywhere, this was extended by Ding, Rishi, Roy, and myself. The same result holds. It works in continuous parameter space. So if you take if you take a continuous GFF and you regularize it at scale epsilon, you would get the same result. It works for certain disordered lattices where globally, macroscopically, it looks logarithmically, but not locally. Still, same result is true. This is joint work with Florian Schweiger, etc. So it's kind of a universal result. Certainly in the Gaussian case, with a family of logarithmic correlations, it is a universal. And although I said I will not talk about the extremal process, there is a very precise, due to work of Biskup and Louisdor, there's a very precise description of the extremes of this process and how do they look. And again, they are not Poisson, but there is an underlying Poisson process, which is randomly shifted behind it. And in development for the last few years is certain nonlinear two-dimensional models, which means they remember that the GFF had this kind of description, which is a Gibbsian description, right? So you have an interaction between values along the neighboring values on the lattice, but there is nothing holy about the square. You could think of all sorts of models, and certain classes of models you can actually couple to the Gaussian one. It's not trivial, and it's highly non-trivial, and it takes effort, but you can do that. And this sequence of papers did exactly that and proved essentially the same type of results. Okay. As I mentioned before, the 2D is important here. Only in 2D you have logarithmic correlation. In 1D, by the way, in 1D, the GFF is nothing but the Brownian bridge. You think about it. It's a Brownian bridge with 0 boundary conditions. The maximum fluctuates at scale square root n. So the maximum fluctuates at the same scale as the typical value. So you definitely don't have this phenomenon. In 3 and higher dimensions, the variance of individual points does not go to infinity. And because of much less correlation, the problem is much easier and everything becomes Poisson-like. So in particular, this quantity converges really to a Gumbel distribution. So all these critical phenomena that occur because of the log do not show up. Okay. So next, I want to move to another example, which is which is, so this is an excerpt from a paper of Wilf on the American Math Monthly. And it's always amusing to me to read that. So it tells a story. I will not read it, but just to summarize the story, it tells a story in the late 80s. He was very happy to finally get a computer home. So he bought these computers that he could program in BASIC and bring it home. And how many people know what BASIC is in this audience? Okay, not bad, not enough nerds. Good. So he could program it and so what he programmed it is to do the following thing: take the screen, which at that time probably had a resolution of, I don't know, 128 by 64 or something like that, or maybe even less, and start with a black screen and start a random walk at the origin. And each time you have these pixels, and each time you go to a new pixel, turn it white. Okay, so you had a black screen, turn it white. So, the random walk starts going. So certainly it will need at least n, if it's an n by n screen, it will need at least n square steps to do something, and n square steps with these computers took maybe a minute, I don't know, something like that. So, and then he says the following: after quite a long while, when the screen is perhaps 95% illuminated, the gross process will have slowed down tremendously, and the viewer can safely go read War and Peace without missing any action, which gives you some cultural references also besides the basic story, etc. And he says, after a minor eternity, every cell will have been visited, the screen will be white, and the game will be over. And his question, and he says, every mathematician worth of its salt would like to know how long will it take for the game to end. Okay, now don't try it at home. If you try to do it at home today, you probably have to insert into your loop a delay loop, because otherwise the game will be over before you start. But okay, so that's a question. And this motivates the following question: for a given finite graph, you can define the cover time to the time for a random walk to visit all the vertices in the graph. And T-curve is a maximal expected cover time, where the maximum is over all starting points. Okay, so that's a property of the graph. Give me a graph, a finite graph, I can compute. And Aldous in the 90s showed that if this expectation is much larger than the heating time, the maximal heating time, or the maximal expected, the maximum of the expected heating time between vertices, then T-curve, the actual cover time, concentrates. Which means you will really have, so it's not always the case, I will not prove it, but if you think about random walk on the one-dimensional ring, this property will not be true. The cover time will be roughly the same as the heating time of two antibodal points. So, but if it is much larger, then T-curve divided by the expectation goes to 1. You should understand that as a statement about a sequence of graphs. If you have a sequence of graphs for which this ratio goes to infinity, then that ratio will go to 1. And then there are two questions. The first natural question is, what is asymptotic of T-curve, and what are the fluctuations? That's okay. So there are bounds. So I will not describe them, but there are some a priori bounds, but not the huge gap. Sorry, I'm running here ahead of myself. Not the huge gap between the upper bound and the lower bound, and this is more or less sharp. So there are graphs for which the lower bound is satisfied. In that case, it's just a coupon collector, and there are graphs for which the upper bound holds. This is the ring I was talking about. Okay, and but so the question is, can you say something more precise? And a breakthrough to that question, although historically this is not how things developed, but conceptually, a breakthrough came through an observation that there is a relation between the Gaussian free field and cover time. And this relation is one way to capture this relation. There are earlier versions going back to Ray Knight in the context of Brownian motion and in more generality to Dinkin. But this is a particularly nice version of this, which says the following. Take a graph. On any graph, you can define a Gaussian free field. So take a graph with a distinguished vertex and define the Gaussian free field with zero boundary condition on that distinguished vertex. So in my previous example of the torus with Dirichlet boundary condition, just think of wired boundary where the whole boundary is set to zero. So it's one vertex. And then what these people showed is that if you look at the local time at the vertex of the random walk until you spend t units of time at the origin, at that distinguished vertex, okay, and you take an independent copy of the Gaussian free field on that graph, a priori a completely different object, they are related by this beautiful form. So there is a relation between quantities that involve only the GFF and quantities that involve a bit of the GFF, that's a PT. If the GFF were not on the left-hand side, it would be much cleaner, but unfortunately, that's not true. It involves a bit of the GFF, but more importantly, the local time. And of course, if you have the local time, you know the cover time, because the cover time is the first t such that LT of V is positive for all V. So there is a link hidden in this formula, but for a long time it was not clear what exactly it is, until this breakthrough of Dingley and Perez came, in which they showed that there are universal constants that relate the cover time with the maximum of the GFF. And shortly after, Ding showed that this constant is 1 for trees and for bounded degree graphs. And with a beautiful idea of using resistance graphs, Alex Jai showed a little bit later that actually for any graph, the constant is 1. So up to leading order, the cover time and the maximum of the GFF are the same. Okay? In particular, on the torus, you have this formula. This is not historically how things have been proved. Historically, the leading order that appeared in that theorem was proved maybe 10 or something years earlier by Dembo, Perez, J. Rosen, and myself, which gave this formula. Unfortunately, it seems to be, at least for the moment, it seems to be the end of the road in terms of fluctuations. You cannot, at the moment, you cannot milk out more information from that isomorphism about the fluctuation, mostly because of the fact that here you have this extra nuisance term that it's not clean local time, but you have an extra convolution of it, and to deconvolve it is difficult. Okay, but anyway, to leading order, we have that. And this was proved by a completely different method. I will come back to it. And that again left over the case of fluctuations. Let me make the comment that in higher dimension, and for a large family of graphs, one do get Gumbel limits for locally transient graphs. And this is a very nice recent work of Berestiki, Hermon, and Teissier. But again, this is a case of less correlation. So I'm always in the most. There is a continuous version of this problem, which instead of working on the discrete graph and looking at the cover time, works on a manifold and looks at Brownian motion thickened by an epsilon ball. So you look at the Brownian motion on a manifold, you take the Brownian motion, you make it into a Wiener sausage, and you're asking how long will it take until this Wiener sausage of radius epsilon will cover the whole manifold. And for the sphere, what we proved in that paper is in the same paper about the random walk is that you have convergence to an explicit constant C star. And about 10 or 12 years later, Bellius and Kistler actually showed that you have a logarithmic correction. So here what was n in the branching random walk story becomes log epsilon here. So you have a logarithmic correction, and this C1 is exactly what you would guess with from a version of the 3/2 that we saw there. And in fact, with Bellius and Rosen, we showed that the difference is tight. And in work in progress, we are, so this should really be posted soon, we can show convergence in distribution, again, to a randomly shifted Gumbel. One remark is that the same theorem holds in the easier case of cover time of trees. So there have been a sequence of works, and in particular, these are the first that gave actually an isomorphism-related proof for the tree. There are isomorphism-based results for modified models, and what is common to all of them is that they inject more independence into the field that kind of masks extra dirtiness from the isomorphism. Okay, so just to say, so this is a state of affair at the moment, that you have this kind of results with a constant C star and C1, which are the correct constants that you would get from the previous picture. And of course, this is done for the sphere or for the torus because it's easier, but this should be true in general, although there is no proof of that. Okay. Let me give now a completely different example. So I switch gears and I'm going to tell you a different story. So suppose I take the CUE. CUE means a random unitary matrix of dimension n, and I'm looking at the log determinant. Okay? And what I want is to look at the maximum of this log determinant on the unit circle. So I have a stochastic process, I have an interval, the unit circle, and I want to find the maximum. About 20 years ago, 20-some years ago, what these people showed is that this process phi z converges to a log correlated field. What does that mean? The variance is actually like log n. It blows up as n goes to infinity, as the dimension goes to infinity. And the correlations are logarithmic. Okay. So you would tell yourself, great, I have this process, it converges to a log correlated field. I know everything there is to know about the maxima of log correlated field. So the maxima of this process should be the same as the maxima of log correlated field. And then you realize that the notion of convergence, when you prove convergence of processes, is much weaker than the notion of convergence for maxima, in particular, especially if you don't prove convergence as process, but rather finite dimensional distribution convergence, which is what is done here. Point-wise, there is no convergence, right? Because the variance goes to infinity. There cannot be a convergence as a process. There's only convergence after you integrate against test functions. So this convergence does not imply convergence of extremes. And that's very lucky because a Gaussian process is symmetric. So if we ask the question about the minimum, what is the minimum of this log determinant? Well, it's a unitary matrix. There are eigenvalues on the unit circle. So the minimum is minus infinity. So if convergence were working, there would be a problem, right? So that's okay. So nevertheless, we have this conjecture of Fyodorov, Hayri, and Keating. I'll come back to the conjecture, which they were motivated by questions about the Riemann zeta function. And there is a well-known analogy, not theorem, but analogy between the Riemann zeta function and unitary matrices or GUE matrices or whatever. And based on that analogy, they did some formal computation, and they gave a very precise prediction for the maximum of this log correlated field. Their prediction is that the maximum minus the log minus 3/4. 3/4 is 3/2 in this context because the variance is 2, but never mind that. Log n converges to a very specific random variable, which is Gumbel convolved with another Gumbel. Right? So, okay, that's a big surprise. But if you believe that, then you see that the maximum should behave like the maximum of the Gaussian free field. Right? You have the same correction and the same sum of two. And indeed, there have been several steps in proving that. So the story starts about 6 years ago. Zargin, Bellius, and Bourgade proved the convergence of the leading order. Elliott, Paquette, and myself, with some hard work, could show something about the correction term, which is the first term in which you see the difference between independent and log correlated. And shortly after, with a completely different method that is much better in a sense and much wider applicable, Shaibi, Madul, and Najnudel were able to show tightness. And recently, with Elliott Paquette, who is here, we could show that not only it is tight, but actually it converges to a convolution of a Gumbel with some other. At the moment, we do not know the W. We have not proved that W is Gumbel. Should be true, but we have not proved. Okay. Very good. Here is another example, Riemann zeta function. So take the Riemann zeta function, which is formally the extension of this expression. And you look at the maximum on the critical axis of the log of the Riemann zeta function. The same paper of Fyodorov, Hayri, and Keating predicted that mt minus t plus 3/4 log t is that, where, I didn't say what mt is. Where is the randomness here? There's nothing random. So how can it converge to a random variable? You take a large interval of size, that's what's written here. You take this huge interval, e to the capital T, and twice that value, and you choose an interval of size 1 at random inside that interval. So you have this huge interval. You take a point at random inside this interval, and you look at a small window of size 1. Okay? And the conjecture is that this guy behaves exactly like the maximum of the G. And in a series of papers of this team and another one here, it was already shown that, first of all, the leading order is what is predicted, this one here, and also an upper bound, which is completely consistent with this conjecture. And my understanding is that the lower bound should be coming out soon. It will not give the convergence, but it will give the tightness. Okay? So again, this seems completely unrelated, but it's the same type of theorem. I'm not going to tell you anything about random polymers. I don't have time. But what I do want to do in the last, 5 minutes that I have, or 7 minutes that I have, taking over time here, I want to explain what is common to all these seemingly disparate problems. So let's go back to the branching Brownian motion. I remind you what it is. You had one particle, exponential clock, it split, they continue to move, etc. So let's look at the maximal displacement at time n. How can you estimate the maximum or the expectation of the maximum? So one method is to say I have the F-KPP, let's solve it. Well, sorry, I'm not a PDE guy. I'm not going to solve PDEs in order to find the solutions. And in fact, historically, the PDE people were able to do it only after they got the solution from Bramson. So it's really not the right way to look at it for me. So what I'm describing now is how Bramson got around to do it, which is a first-second moment method. So what is the idea? The idea is if I want an upper bound on the displacement, what I can do is to compute the expected number of particles above a certain level by time n. And this is essentially e to the n times the probability that the particle is larger than x, and you get this expression. And you will recognize that this expression is the same as you would get for independent variables. So this is assured not to give you the right answer. But bear with me. Let's accept that. So if x is larger than this quantity, then this goes to 0, but this is the wrong answer. However, there is no reason to apply this reasoning only at the end point. I can apply it at any intermediate time. So if I look at the intermediate time, I can see that, in fact, my maximal particle at any intermediate time is smaller than c star t. Okay? Which means that all particles that I care about should be below this straight line. Right? Because I cannot go above this straight line. Cheating a tiny bit here, and it's an exercise to see where I'm cheating. So I'm not going to reveal it. You can ask me after the lecture. But now, if you ask for a single particle, what is the probability that a single particle is below this straight line? The answer is not going to be e to the minus x squared over 2n divided by square root n, like it is for Gaussian, but it's going to be that divided by n to the 3/2. Okay? And that's a barrier problem. If I constrain Brownian motion to be below a straight line, and I want it to start essentially near 0 and end essentially near 0, the probability that it does it is not 1 over square root n, but 1 over n to the 3/2. So this is a better upper bound. And if you substitute it, you find Bramson's result. So that's the upper bound of Bramson's result comes from that. Just from adding this extra constraint that a priori you could get from a rough bound. And now, once you have this constraint, you can put in this constraint. It turns out that with this constraint, the second moment of the total number of particles that does that is essentially the first moment squared. The point is that this extra constraint reduces the variance of this sum by a lot. So this is essentially how it was done. And for convergence, you need to work harder, but I don't have time to go and explain that. So the question, okay, so what we saw is that we have a method, first moment of the number of particles above a certain a priori, that satisfy a certain a priori bound, and then second moment of the same number. And why does that have anything to do with, I'm taking a few moments. So why does that have anything to do with all these problems I told you? So one remark is that the Gaussian free field on the tree is exactly branching random walk on the tree. If you think about the definitions for a moment, if I take on a tree, there are no loops. So this expression for the GFF is just a product of independent variables. So it means on each edge of the tree, you put an independent variable. That's exactly a branching random walk, and you're summing them as you go. So the increment on each edge is just an independent random variable. And then you look at the bottom of the tree, so that's exactly a Gaussian free field. So there is a Gaussian free field here. For the discrete Gaussian free field on Z2, well, this is not true. Well, you do have the Markov property. And the key turned out to be to use a Gaussian property and actually compare that field to a tree and to a modification of a tree. For general Gaussians, you have to work harder on the modification, on the comparisons, but it's essentially the same idea. What about cover times? Well, instead of looking at cover time, what you can do is count excursions. So if I take a point here, I want to cover this point. What I can do is keep track of the number of excursions between concentric circles. And the property of dimension 2 is that if I take a random walk and start, if the ratio between these circles is the same, okay, then the probability to go down and the probability to go up is 1/2. So I really have a random walk, and I'm counting how many times it goes up or down, and this will be the number of excursions. So the number of excursions satisfy a recursion, which is like a random walk. And then I can say, well, what points do I care about? I care about points that are uncovered. So it means that they have 0 excursions at the lowest level. But if a point is uncovered, I can look at the profile of excursion along the way, do the same type of a priori estimate as I did for the random walk, and say a point is successful if the number of excursion along the way is this particular profile. Okay, which corresponds to following the straight line when you do the translation between the excursions and the random walk. So that's great. I have again a lot of points. I have a first moment which with this constraint that it follows this straight line and does not go over it. And if you work and do the machinery, it will be the same, except that, of course, what I used on the tree is that at level t, I only had e to the t points. On the lattice, that's not true. Even if I look at excursions on big balls, it is not true that I have only to consider a smaller number of big balls. But there is some kind of continuity. So there is a hard work in showing that the continuity you get is good enough that allows you to reduce at level t the combinatorial explosion to be roughly e to the t and not e to the log n. So that's kind of the idea. And now, where is the tree structure for the excursions? Well, that's actually easy to see in this kind of the snake in the Mowgli. So if you look at 2 different circles, then you realize that once you go to a distance which is about the distance between the radii, the circle that the large circle around this point and the large circle around this point are essentially the same, which means that they share a common history up to the splitting. And that's exactly a branching contour. So, okay, of course, the technical details are much, but okay, and for random matrices, at least this is one way that turns out to be more efficient ways of doing that. You can look at the log determinant not on the circle, but going inward into the circle and looking at the differences of this log determinant. This turns out to be roughly independent variables and roughly Gaussians, and you can play the same type of game. And if you go this route, you have to evaluate correlations in a very precise way. And okay, this is not, eventually this is not the way, but I will discuss this example next week in more details, and you will see that it's a very different approach eventually. And I don't have time to do that, but you can say a similar story for the Riemann zeta function if you are willing to do the usual heuristics in which you model the primes as independent points. So if you believe that heuristic, then you get immediately a log correlated structure, etc. And all the hard work is to show that the correlation structure from the non-random object is essentially the same as the one for the independent. Okay, so I will stop here and thank you for your attention.
Thanks very much to Ofer. Are there any questions or comments? So, okay. So do you think there are other examples where?
Oh, yes.
Yes.
There are zillions of other examples. So one on which I'm thinking currently is about nonlinear models, but which are related to the GFF, but which have a nonlinearity, what is called Ginzburg-Landau models. So you have a nonlinearity there. So there, the leading order has been computed. We have subsequential tightness, and we are working on getting more refined estimates. The Gaussian tools disappear. There are some other tools, but they're not, I mean, you have to work much harder to make them work. There's a story about polymers that I did not discuss it. Again, you have a low correlated field. So yes, I'm sure there are lots of other examples.
So in this Ginzburg-Landau, is there some tree structure again that comes up? Or
so you would, the Markov structure gives you a tree structure, because what you can do, and that's also true for the GFF, you can in principle divide your box into dyadic sub-boxes, and this gives you a tree structure.
Okay.
The problem is that you don't have, what you're adding is not independent for different points. It's kind of related, so you have to get a handle on that.
Yes. Wait.
Do you think there should be a unifying framework for all of these results?
Okay, so it depends what you mean by unifying framework. So at least in the proofs as I have described them here, there is a unifying ideology, which is to prove certain good continuity estimates that compare to a tree or to a tree structure, and then you get everything. But the problem is that in all this, it really depends on the problem to be able to do this comparison. And it's yeah, I guess it's $1 million question. Can I look at a nonlinear problem? So for Gaussian, we did that, right? For Gaussian, we have a unified theory. It says if your covariance, because the Gaussian is really characterized by a simple covariance. But all these problems, when you look at them from afar, they look very, very different. So you have to find the hidden tree structure, and you have to find that you're close to it. And I don't know how you could do it without going to the details of the system. Now, I should say one more thing, that the additive constant that appears in the shift, in the random shift, it comes always from the coarse scales. So in the tree, it comes from the beginning of the tree, which is the thing that creates longer range correlations. Okay? In fact, this constant, we know exactly what it is in the tree. It is related to a derivative martingale. So it's really something that comes from the beginning of the tree. Same thing for cover time. It's something that comes from what the random walk did in a very coarse scale. And for the cover time on the tree, same story for Ginzburg. So in all these stories, that random variable is very problem specific. Okay, it's very much non-universal. So the theory is universal, but the details are very much not so.
Maybe one more question. So of course, you're using the Markov. So do you think this actually works in any non-Markov settings?
Well, all these problems are, I mean,
yeah.
the Gaussian model is not Markov. It's just a correlation structure. There's no Markov.
Yeah, but non-Gaussian, non-Markov.
The cover time itself is not Markovian. If you look at the cover time or at the local time, it's not Markovian if you look spatially. Yes. So all these models are very roughly Markov, but not precisely. Mm-hmm. So that's really what I can say. They are close to a Markov model, but they are not.
Okay, are there any other comments or questions? If not, let's thank Ofer once again for a very nice talk.